Hi, this is Jose Luis, and welcome to another video on this series Introduction to Parametric Modeling, where this video is going to be a hands-on exercise on creating a facade that has some kind of design that involves optimization for some kind of environmental parameter, such as, for example, the incidence of the sun. Because as far as we have done so far, we know how to take a surface and then subdivide that surface into a grid of elements and then populate it with, for example, a set of circles. The circles could be, for example, openings. They could be the windows of a hypothetical facade of a building. But these openings could actually be somehow optimized for a particular condition. Like, for example, the incidence that an external agent, like the sun, could have over this facade. Because what we can do is we can calculate how the sun is hitting each one of the points of that facade. And based on that calculation, what we can do is we can optimize some of the openings and change their size so that the ones that are directly frontal to the sun are smaller. Let's imagine this is a warm climate. And the ones that are somehow tangent, kind of tangent to the incidence, they have a bigger opening. And therefore, we can now design a facade that as we change where the sun is, then the openings adapt. This could work for the design of a facade, or it could work also for a facade that has windows that open and close throughout the course of the day. I don't know. There's many applications that we could do about this. So we're going to create this kind of facade that is parametrically adapted to the incidence of the sun. And you're going to see that the exercise is actually going to be super simple. It's a very small one. It just involves a little bit of thinking ahead. What does sun incidence mean in terms of geometry? It's going to be super simple and a lot of fun. Let's get to it. Let's get hands-on. All right, here we go. Let's get started. This exercise is going to be a lot of fun. You're going to see. I like this exercise a lot. So what are we going to do? So we're going to imagine that we're starting with some kind of free-form facade. I'm designing like a really fluid building of sorts. And then what I want to do is I want to optimize some openings in the facade of this building. And how is that going to work? Well, we're going to imagine that this building is going to be situated in some kind of very warm climate. And what happens in warm climates is that typically one of the things that you want to avoid is that you don't want to have a lot of direct sun incidence on your facade or going through your openings into the building, because that brings in a lot of heat inside of the building, and what you typically want to do is to keep the building as cool as possible inside. This is the condition for warm climates. For cold climates, it's a really different story. So the logic here would be, I want to design some openings that are optimized for the sun incidence, okay? And optimization in this case will be very related to the fact that I will want to have some of the openings be bigger wherever there is less direct sun coming in from the facade, so that I still get light, but I don't get direct sun and I don't get heat inside of the building. And then the opposite will also be true. In those areas of the facade where I have a lot of direct sun incidence, those will have the smaller openings. And how can I do that? So that's actually going to be fairly easy given the tools that we already have in our tool set. So what we're going to do is we're going to do some kind of analysis where we're going to imagine that we have the surface. This is going to be like a section of the surface. We're going to imagine that we have a sun, and for this analysis we're going to imagine that the sun is always on the same place, which is not the case. The sun is rotating over an arch and it changes inclination over the year. So the real problem is actually much more complex than we're going to do here. But we're going to imagine that we have a static sun that is always on the same position. And what we're going to do is we're going to subdivide the surface that we have into the center points of where we plan to put these openings. And then we're going to do a very simple process where we're going to cast virtual rays from this virtual sun into each one of the points. And then we're going to calculate the angle between the ray of the sun into that particular point, and then the normal, the perpendicular vector from that surface to that surface from that point. And it turns out that if that angle is very wide, then the solar incidence of the facade will be very small. And then that opening will be able to be rather large. But as soon as the inclination of the surface starts pointing towards the sun, or in other forms, as soon as the angle between the sun and the normal to the surface at that point gets smaller, then the stronger the sun is hitting that opening. And therefore, the distributions of the openings will be proportional to how little the angle is. So the larger the angle, the larger the opening, and the smaller the angle, the smaller the opening as well. So in a nutshell, that is the process that we're going to follow. We're going to subdivide the surface into a bunch of points in the UV direction. We're going to calculate the normals to the surface at each one of those points, and then we're going to calculate the angle between the sun and each one of those vectors. And then, given that value of the angle, we will design openings on that facade that will be proportional to that angle. Let's take a look at how to do that in a simple way. So let's get started. So we're going to imagine that I have some surface that I have in Rhino, that I have designed, whatever, or this may actually be a surface that comes from some kind of parametric process that you have done in Grasshopper. It doesn't really make a difference. So if you had a component with a surface, you would plug that component all the way into the beginning of this definition. Otherwise, what you can do is you can just click surface, then right click, and then set this surface as the input parameter that we're going to start working with. So no matter if it comes from Rhino or Grasshopper, it doesn't matter. We have the surface as data, and then we can start working with it. So the first thing that I'm going to do is I am going to divide this surface into a grid of UV points. So I could do that with the divide surface, which, if you remember, it gives me the points and the normals and the UV, and because I want the normals, this is kind of good. But you know how I like working with planes better, and we will actually need those planes at some point farther down the road. So I'm just going to opt for surface frames instead, and then what I would like to do is I would like to subdivide this into a grid of UV planes, and that's going to be, for example, I'm going to say that this is going to be 10 and 10, and actually no, I'm going to do a little bit more than that, 15 and 15 in each direction, so U and V, and then this is going to, maybe something like that, or maybe a little more, maybe a little more dense. We can probably go a little more dense. Okay, so something like that. So these are going to be where the openings of my facade are going to be. Okay, so those are going to be the centers. And then, as we said, we are going to need to find the normal vectors on each one of the centers of my facade to the surface. So because I did frames, frames contain all the possible information. They contain the orientation, the center, but they also contain the normal. And because they are planes, so something that we can do is we can, if we want to actually extract the normal vector to start working with it at some point, what we can do is we can go to plane, to vectors, we can go to planes, and then here, just like we could construct and deconstruct points and vectors, we can also construct and deconstruct planes. So if we use the deconstruct plane component, you can see that this component takes a plane, and then what gives me in result is the origin point, the x-axis vector, the y-axis vector, and the z-axis vector, which is the normal. Just to make sure that this is what I want, I'm going to turn off this visualization. I'm also going to turn off these points. And what I'm going to do is I'm going to visualize those vectors with a vector display component. We've used this in the past, and this vector takes the vector, I want to visualize V, but it also takes anchor points. So the anchor points, I'm going to take the center of the plane, which is also given to me here in the, and you can see that indeed I am getting arrows that are sticking out of the surface, and they are perpendicular to the surface, which is kind of very nice. Okay, dokie? And if I wanted to make, for the sake of visualization, if I wanted to make those bigger, I could just take the vector and set the amplitude to a larger value and then visualize that larger vector. I don't know, just for visualization. Okay? Wonderful. So I have the perpendicular vectors to the surface. Then the next thing that I need to do is I need to calculate the distance to, I need to calculate the angle with a sun object. So for that, I'm going to have to model the sun. How are we going to model the sun? Like a big fat sphere? I mean, we could do that, but it's a little pointless because at the end of the day, what we're interested in is where the sun is in 3D space. And for that, the only thing that we need is actually a point. With a simple point, we can model, theoretically, we can model where the sun is. So I'm going to create a point here that I'm going to create in Rhino. And then I'm going to bring that point here into Grasshopper by adding an empty point component and then just loading it into Grasshopper, okay? Then the next thing that I need to do is for each one of the points that I have here on the surface, I need to calculate the incidence vector from the sun to each one of those points. So that's going to be as easy as taking a vector and creating a vector between 2 points. The first point being the sun, the virtual sun that is defined by this point, and the second point being all the centers of the planes that I have deconstructed before. So those are going to be the origins here. And as soon as I do that, I have my vectors, and just for the sake of visualization, I'm going to use a vector display. The vector display is going to visualize all these vectors and is going to anchor them on the first point. So on this point, on the sun, we're going to see all those vectors hitting the surface of hitting the points of the surface. Can you see that? Beautiful. And then the only thing that we need to do is we just need to calculate the angle between these two. We could do hardcore vector algebra for this, but Grasshopper gives us an easier way to do that, which is if you go to vectors and you go to vector here, you can calculate the angle between two vectors. So that is going to be the angle between two vectors is going to take A and B, the first and the second vector, and an optional plane if the angle that I want to measure is in a particular 2D plane. Otherwise, the angle will be in pure 3D. So I'm going to turn all of this off, and then I'm going to measure the angle between the incidence and the amplitude here. Sorry, not the amplitude, sorry, the C vectors here. And then this is going to give me a set of angles that are going to be roughly about this. These are angles in radians. So if I want to see those in degrees, I can just go to the Math tab and go to Trigonometry and then turn an angle from radians into degrees. So this will be these angles here. Now, one interesting fact is that all the angles are larger than 90 degrees. Can you see this? And it is so because if we go to the diagram, we can see that the angles that we have here on the right-hand side, where are the angles? We can see that I've actually made a mistake in the way I have drawn the angles on the diagram, because if you look at this diagram carefully, the sun is a vector that is coming this way, right? Sorry, the sun is a vector that is coming this way, which means that the actual vector is something like this. And the angle between this vector and the normal is this angle here. So that is the real omega. Whereas here, if this is the sun, this would be the real omega, which is smaller, and this is going to be the real omega, which is even smaller. So because that's the case, this is the real angle between them. And then the rule in this case will be that the smaller the angle we have, the larger we want the opening, and the bigger the angle, like in this case, then the smaller the opening. All right. So it's always good to look at the numbers and to review, because you can see that I made an assumption that wasn't really correct as from a diagrammatic point of view. All right. So what are we going to do this? What are we going to do with this? Well, what we now want to do is we now want to use this information, the angles, to make decisions about how big the circles that we're going to place on these openings are going to be. So I'm going to, for example, I'm going to start by drafting what this is going to look like. So I'm going to place some circles, and I'm going to place the circles here on the surface frames. Okay? So because the circles take a plane in order to get drawn, you can see how the circles are kind of aligned with the surface. So that's one thing. And I can see that if I drop a slider here, I can control uniquely the size of each one. But that's not what we want. What we want is to use those values, the values of the incidence of the angle. We want to use those values to affect how some of the circles are going to be bigger and how some other are going to be smaller. Okay, so what we're going to do is we're going to do a very simple numerical transformation, so that what we're going to do is that we're going to normalize all the values of those angles into numbers that go from 0 to 1. And this process is typically called normalization, and it's a very useful process because once you take a collection of numbers that can have some range, and then you shrink it or you expand it to be within 0 and 1, working with these numbers is typically much easier. So for example, let's take a look at the possible scenarios that we have with the sun incidence. So let's say we have a facade that was purely circular, okay? Something like this. And then we have the sun that is hitting this way. What possibilities can we have? Well, if we have a point here, right, on this facade, and the sun is hitting this way, and the sun is hitting this way, then the incidence vector looks something like this. So that's the vector. And then we have here the normal vector sticking out, so the angle is going to be 180 degrees. Okay? So that is the worst condition that we can have, which is when the sun is hitting exactly the facade in the most frontal way. Now, we can have some intermediate point here, and then the sun is hitting something like this, and then the normal is something like this, so maybe this is 135 degrees, I don't know. Then we have the intermediate scenario, which is that the sun might be hitting in a tangent way to the facade, okay? And then what we want to do is we want to look at the normal and say, well, this is 90 degrees. Okay? So that is the best possible scenario, which is that the sun is not hitting the surface whatsoever. It's just perfectly tangent. And then on top of that, we actually have other scenarios, which is if the building is cylindrical or spherical, we have this situation which is not really exactly like this. The sun is never going to hit this face, but from a computational point of view, we do have this in the data set. So that would be 45 degrees, and then this point here would have the sun here, and would also have the tangent here, and then this angle would be 0 degrees. So what we want to do is we want to make sure that we account for all these possible scenarios. And then we want to have a rule. We want to write a rule where if this is a situation we have a 180 degree incidence, so purely strictly perpendicular, we want to associate this to the value of 0.0. We're going to call that the opening factor. And then if the sun is hitting the surface at 0 degrees, so completely perpendicular in the other direction, that is going to be the best case scenario, which is 1.0. Okay, so which is going to correspond to this. And then any angles in between that are going to have intermediate values. Like for example, this would be 0.5, this might be 0.75, and this might be 0.25. The idea is that with this, oh, sorry, no. So it would be the other way around. So this would be 0.25 and this would be 0.75. Yes, the idea is that what we want for ourselves is to come up with a numerical range that is easy to manipulate. And this is very typically from 0 to 1, and therefore we can feed that into other kinds of calculations. And this factor, 0 to 1, is basically telling us how perpendicularly the sun is hitting our surface. So once we're able to generate that number, which we're going to do with a very simple operation, then we will be able to use that number to derive the openings or the closings of the facade windows. Let's take a look at how to do that. We're going to go back to Grasshopper, and then we're going to take all these angles here. These are the angles, and instead of from 0 to 180, they are going from 0 to pi, because they are in radians. So we can work with, we can convert them in degrees if it's easier, or we can work directly in radians. Let's work directly in radians because we've done we've done like degree conversions already for a little bit. So the way we're going to do this is, remember, we want to rewrite this so that numbers from 180 to 0 become numbers from 0 to 1. In a way, we're also going to flip the order, okay? So we can do that with a mathematical operation that is called remapping. How does that work? If we go to math and we go to domain, we have a component here that is called remap numbers. And the way this works is that it takes several things. It takes the number you want to remap, but then it takes what is the source domain, so what is the range that these numbers are coming in from, and then T is going to be what is the domain that you want to change these numbers to. So as we said before, we're going to create here a new first domain, and the input domain, as we said, are the angles between 180 and 0. So what we want is, we're going to go here and we want to say the input domain is going to be a value that is going to start at 0 and is going to go to the value of pi, because remember we're going to work in radians. So pi actually has its own component here. This component gives us the value of pi or a factor of pi. So we want to remap our numbers, and the domain, so the range, the interval at which they are, is from 0 to pi. That is going to be the input. And then what we want to do is we want to say the target domain needs to be a new domain. Sorry, I'm going to construct a new domain, and the new domain is going to go from 0, it's going to go from 1 to 0. Because remember, when we are at 0, sorry, oh, I'm making a mess out of this. Sorry. Sorry, when we go from 0, and when we are at 0 degrees, we want a factor of 1. And when we are at 180, we want a factor of 0. So that's why when we are at 0 degrees, we want a factor of 1. But when we are at pi radians, we want a factor of 0. So that's why we're doing this here. And then what we're going to do now is we're going to remap all of these values. So these are the values that we want to change from the two different domains. And let's take a look at what that looks like. It looks to me like this is working because the higher the value in radians of the angle, the smaller the factor. So you see how the angle becomes smaller and the factor becomes larger. And when we are at 1.5, which is more or less half pi, we are at 0.5, which is halfway to the factor. So this is great. So I think we are in a good position now to plug this into the circle and see if this works. So let me turn on the angles and the vectors. We have the sun. I moved it a little bit farther, closer to the surface, so that it was easier to see that this part here was very frontal. So this part here is very frontal, and this part here is rather perpendicular. So we can see that here, in this area, the openings are larger than here in this area, which is a bit more frontal, where they are closer. And this area is very, very clearly super frontal to the point, and therefore the values are very small. But how big or how small? Well, right now they go from 0 to 1, literally, because it's the remapping. But if we wanted to factor those, I can just multiply those values for some kind of arbitrary value. So for example, I can just open up this and make them twice the size, for example, or make them 3 times the size, or 4 times the size, or anything, you know? So, and then now with these circles, what I can do is I can create, for example, a planar surface, which is somewhere here. Where is this? I can't see it right now. So, planar surface, boundary surface, for example, here. And then I can get that, and then I can just hide this. I can hide this surface here, and then I can remove this too, and then I can also hide this surface, and you can see how the openings for this facade are now corresponding to the angle. And if I move the sun, you can see how these guys, these windows are becoming bigger, these are becoming smaller, you see? And you see how now these windows are super big and these ones are much smaller, right? How awesome is that? And now we have a facade where every window has a size that is exactly fitted or optimized for the best sun incidence. Well, that's a huge statement, so it's not as simple as that. There's a lot more calculations, but this is the basic core of this is the basic gist of the problem. Okay. All right, wonderful. So that was designing a facade that has some kind of optimization for solar incidence. I see we got a little spaghetti-ishy here, but with a little bit of cleaning up, this can be much more legible. And of course, we can always like more count, less count, more in one direction, more in the other direction, etc., etc. So that can be parametrically customized. All right, wonderful. So I hope you enjoyed this exercise. This was a parametric solar facade. This was Jose Luis. This is Parametric Camp. And this is the series Introduction to Parametric Modeling. Let's move on to the next video where I'm going to do another exercise that is also going to involve some kind of solar analysis / being aware of where the sun is and try to optimize some kind of orientation. In the meantime, if you had fun, if this was helpful for you, maybe consider liking this video, subscribing to the channel, and all those things that we do these days on YouTube. Thank you very much, and see you on the next video. Bye.